Hi, I'm Dr. G. Glory, Associate Professor of Physics, Institute of Aeronautical Engineering. Today, I wish to tell about the principle and construction of an optical fiber. So, this belongs to the third module in our lasers and fiber optics, which is in applied physics. So, in this principle and construction of an optical fiber session, we are going to cover the topics: introduction of optical fiber, and then we are knowing about something basic idea about the optical fiber and working principle of optical fiber, how the optical fiber works, what is the principle what is the principle in this optical fiber, and then we are going to see conditions for propagation of light through optical fiber. Then finally we are going to see the structure and construction of optical fiber. So these are the topics we are going to cover in this session. Let's see the introduction. So generally communication is transferred through carrier wave. Communication is transferred through carrier wave in any communication system. If we take any communication system, the communication is transferred through the carrier waves. So when the frequency of the carrier waves are high, then the information carrying capacity also be enhances. So when the frequency of the carrier waves are high, then information carrying capacity also be enhanced. So as the propagation of light takes place in the form of high frequency waves, these light waves can be used to carry information as carrier waves. So for the proper guiding of information carrying light waves, we need a proper guiding material or guiding medium. So that material or that medium is the optical fiber. So to carry the information through light waves, so we need a material to transfer. So that for the proper guiding of information carrying light waves, we need proper guiding material. So that material is the optical fiber. In this optical fiber, it is a guiding medium or material which guides the information carrying light wave. So the light wave is carrying some information, so we call as carrier waves. So which the light waves are carrying some information. So this information carrying light waves can be guided by the medium or a material called the optical fiber. So that optical fiber is a guiding material which guides the information carrying light waves. So to guide the light waves, optical fiber should be transparent. So to guide the light waves, optical fiber should be transparent. So to minimize the transmission losses, here there is some losses are there due to long distance traveling, long distance or bending. So to minimize these transmission losses through the optical fiber, it is made thin. Thus, optical fiber is a thin and transparent guiding medium or material which guides the information carrying light waves. So, optical fiber is a thin and transparent guiding medium or material which guides the information carrying light waves. John Tyndall observed that the propagation of light through the optical fiber will be in the form of multiple total internal reflections. So, he observed, that is John Tyndall observed that the propagation of light through the optical fiber will be in the form of multiple total internal reflection. Multiple total internal reflections. Even in the bended optical fiber also. Even in the bended optical fiber also, it is in the form of optical um, fiber, that is in the bended optical fiber also, it is in the form of, that is the light will be passes in the form of multiple total internal reflections. So as the information carrying capacity light waves are high, single optical fiber can carry 140 megabytes of information up to 220 kilometers in 1 second. So what is the working principle of optical fiber? Optical fiber consists of innermost layer known as core. Here there is a layer which is inside. So optical fiber consists of innermost layer known as core. A denser medium, and the next layer is known as cladding, or a denser medium, and the next layer is known as a cladding, a rarer medium. So here the innermost layer is the core, and it is a denser medium and surrounded by a cladding which is a rarer medium. So consider an optical fiber consisting of a core and cladding of refractive indices N1 and N2 respectively. So we are considering an optical fiber which is consisting with the core and cladding having refractive indices N1 and N2 respectively. So refractive index of the core is N1. So N1 is greater than the refractive index of cladding, which is N2. So refractive index of core is N1. Refractive index of cladding is N2. Here N1 is greater than N2. So refractive index of core is greater than the refractive index of cladding. Now let a light ray move from core to cladding. Core to cladding medium with the incident angle I and angle of refraction R. So here a light wave move from core to cladding with angle of incident I and the angle of refraction R. The refracted ray bends away from the normal. The refracted ray or the refracted ray bends away from the normal as it travels from core to cladding with increase of angle of incidence. So the refracted ray bends away from the normal as it travels from core to cladding with increase of angle of incidence. Here we get three cases. Here case 1 is when I is less than theta c. The light ray refracts into the core. So when I is less than theta c, that is I is the angle of incidence. I is the angle of incidence. Theta c is the critical angle. theta c is the critical angle. So here in the case 1, so when these three cases are happening, when the refracted ray bends away from the normal as it travels from core to cladding with increase of angle of incidence, we get three cases. First case is when I is less than theta c. The light ray refracts into core. Refracts into core. That is, angle of incidence is less than the critical angle. The light ray refracts into the core. In the second case, when I is equal to theta c. When I is equal to theta c, then the ray traverses along the interface of the core and the cladding. Okay, so when I is equals to theta c, that is angle of incidence is equal to the critical angle, then the ray traverses along the interface of the core and cladding. So theta c is known as a critical angle and the refracted ray as critical ray. Coming to the third case, when I is greater than theta c, angle of incidence is greater than the critical angle. Then the light ray will be reflected back into the core and undergoes total internal reflection. When angle of incidence is greater than the critical angle, then the light ray will be reflected back into the core and undergoes total internal reflection. So for core and cladding, by applying Snell's law, we get N1 sine I is equal to N2 sine R. So what is this I and R? Angle of incidence. N1 is the refractive index of core. N2 refractive index of cladding. I is the angle of incidence. R is the angle of reflection. Okay. N1 sine I is equals to N2 sine R. This is by the Snell's law. So when I is equal to theta c, when I is equals to theta c, that is the angle of incidence is equal to critical angle, then R, the angle of refraction is equals to 90 degrees. Angle of refraction is equal to 90 degrees. Therefore, N1 sine theta c is equals to N2 sine 90 degrees. So, here I is equals to theta c. So that replacing I as theta c. So here N1 sine I is equals to N2 sine R. So where here I is equal to theta c. So as I is equals to theta c, N1 sine theta c is equals to N2, and when I is equals to theta c, R becomes 90 degrees. So that sine R, sine R, so sine 90 degrees. Now we want the critical angle, how much? So N1 sine theta c is equals to N2. N1 sine theta c is equals to N2. So N1 sine theta c is equals to N2. From this, Sine theta c is equals to n2 by n1 is implies theta c is equals to sine inverse of n2 by n1, which we got here. Here n1 is greater than n2. Okay, so theta c, critical angle theta c is equals to sine inverse of n2 by n1. So the conditions for the propagation of light through optical fiber. So what are the conditions for the propagation of light through the optical fiber? So first one, when the incident light makes an angle greater than the critical angle at core cladding interface at the top of the fiber, it will be reflected down into the core due to total internal reflection. Suppose is the core. This is surrounded by cladding. So here the refractive index of core is N1. Refractive index of cladding is N2. Here N1 is greater than N2. So when the incident light makes an angle greater than the critical angle. So incident angle is critical angle I is greater than theta c. Then what happens? The light ray entering into the core, when it hits or encounters the interface of core and cladding, at the top of the optical fiber, it will be reflected. It will be reflected down into the same medium. So it is entering into the core. When it encounters the interface between core and cladding, it reflected down into the core due to the total internal reflection. When the reflected light strikes the core and cladding interface at the bottom of the fiber, again it will be reflected up due to total internal reflection. So now because of I is greater than theta c, when it encounters the interface of core and cladding at the top of the optical fiber, it reflected down into the core, and then when it strikes the core and cladding interface again at the bottom, then it up the light ray again reflected up due to the total internal reflection. So thus the propagation of light will be in the form of multiple total internal reflection through the fiber. So the propagation of light will be in the form of multiple total internal reflection through the optical fiber. Now we shall see the structure and construction of an optical fiber. So before that, we have seen the principle of optical fiber. So what is the principle? The principle of optical fiber is the total internal reflection. Based on the total internal reflection, the optical fiber works. In this working principle of optical fiber, so let's we are taking case 1, case 2, case 3, that is the optical fiber works on the principle of total internal reflection. What is that total internal reflection? So here, when the refracted ray bends away from the normal as it travels from core to cladding with increase of angle of incidence, there is three cases. That is, first one is I is greater or less than theta c. In the next case, I is equals to theta c. Third case, I is greater than theta c. So, I is the angle of incidence, theta c is the critical angle. So, here, light ray is entering from denser medium to rarer medium. So, the refractive index of the denser medium is N1, refractive index of the rarer medium is N2. Suppose the light is incident with some angle I, so it refracts away from the normal. So this is the normal. So it refracts away from the normal. Refracts away from the normal. It refracts away from the normal. So this is the angle of incidence I. So this is when theta is, I is less than theta c. Okay. So when I is equals to theta c, what happens when I is equals to theta c? So light is incident with some angle, incident ray. So incident ray. This is the normal. Here, a refracted ray bends away from the normal as it travels from core to cladding with the increase of angle of incidence. So, when I is less than theta c, what happens? The refracted ray bends away from the normal. Bends away from the normal. Bends away from the normal. Here, when I is equals to theta c, the instant ray, when it incident with some angle at the interface, it lies on the refractive angle moves away from the normal, so it lies on the interface between the two medium. Interface between the two medium. So when I is equals to theta c, the refracted ray lies at the interface between the two mediums. So that's why I is less than theta c. Suppose this is the core, this is the cladding. So I is less than theta c. Here we are going to apply the same. So here, when I is equals to theta c, ray traverses along the interface of the core and cladding theta c. When I is greater than theta c, so I is greater than theta c is the normal. So increasing angle of incidence I. When increasing I is equals to I is greater than theta c. I is greater than theta c. What happens? The incident ray reflected back into the same medium. Back into the same medium. That is into the same medium. So this is the okay. This is refractor ray. Refractor ray. So when it encounters, here when I is greater than theta c, the light ray reflected back into the same medium undergoes total internal reflection. Based on this principle, the optical fiber is worked. Here in this condition, so how the propagation of light through the optical fiber is happening, and what are the conditions for the propagation of light through the optical fiber. So that here for an example, I'm taking inner layer as core, outer layer as clad. So this one is core, and it is surrounded by cladding. Core is surrounded by cladding. So the refractive index of core is N1, refractive index of cladding is N2. So light is, suppose this is the fiber axis. Light is entering with some angle. So when it encounters the interface between the core and cladding. So as here I is greater than theta c, so the light ray totally reflected back into the same medium. Again, when it encounters the interface of the core and cladding at the bottom, it reflected up into the same medium. Again, it encounters the interface core and cladding. So again, it reflected back. So like that, total internal reflection happens in the optical fiber. So propagation of light will be in the form of multiple total internal reflection through optical fiber. So when we are going to structure and construction of an optical fiber, it is a very thin flexible thread of transparent plastic or glass in which light is transmitted through multiple total internal reflection. So an optical fiber is a very thin flexible thread of transparent plastic or glass in which light is transmitted to multiple total internal reflection. So it consists of a central cylindrical layer known as core, which is surrounded by a second layer called the cladding. So the core is the inner part of the optical fiber which guides the light. So here the core is the inner part of the optical fiber. So this core guides the light. So the cladding surrounds the core completely. The refractive index of the core is higher than the refractive index of the cladding. So core acts as a denser medium and cladding acts as a rarer medium. So light in the core that strikes the boundary with the cladding at an angle will be reflected back into the core by total internal reflection. So as we are taking with that type of conditions, that is N1 should be greater than N2, I is greater than theta c. so that the core acts as a denser and cladding acts as a rarer, so that light in the core that strikes the boundary with cladding at an angle will be reflected back into the core by the total internal reflection. So here we are going to see the various parts of optical fiber. Various parts of optical fiber. So core, innermost layer, core. Core is the typical cylindrical glass material of having diameter 50 micrometers surrounded by a which is surrounded by a cladding. Clad is a glass material which has slightly lower refractive index comparing to the core, and the overall diameter of this core and cladding overall diameter is 125 micrometer to 200 micrometer. So here the core and cladding both are usually made up of same glass material or the same plastic, but to keep refractive index up, if clad lower than core, some impurities like boron, phosphorus or germanium are doped. So like that it prepared. So the core and cladding. So here we have mentioned that it is a glass material and this is also a glass material. But the refractive index of these two is different. So N1 is greater than N2. So core refractive index is N1, cladding refractive index is N2. So refractive index of core is core should be greater than the refractive index of the cladding. So that to prepare such a way that both are prepared or both are made up with made up of glass materials only. But to keep this refractive index, that is N1 is greater than N2, some impurities will be added to the cladding. So that is boron, phosphorus or germanium, like that type of materials impurities can be added to the cladding to lower its refractive index. So next one, silicon coating. So it is provided between clad and buffer jacket. So between the clad and buffer jacket, there is a silicon coating which is used to improve the quality of transmission of light. It improves because of the silicon coating, there will be improvement of quality in the transmission of light. Next one, buffer jacket. So this buffer jacket is covered over silicon coating. So this is made up of a plastic material and protects from moisture and abrasion. Buffer jacket is covered over the silicon coating, and this buffer jacket is made up with plastic material and it protects from the environmental issues, that is moisture or abrasion. Strength members. This layer is arranged over the buffer jacket to provide necessary toughness and tensile strength to the optical fiber. So strength members, there is a layer that is arranged over the buffer jacket to provide necessary toughness and tensile strength to the optical fiber. And then there will be outer jacket. This is the final one, that is a final black polyurethane layer. It is provided to avoid damages during hard pulling, bending, stretching or rolling of the optical fiber in the real field. So to protect this optical fiber, there will be again outer jacket, so which is made with black polyurethane layer. So to avoid the damages during the pulling, bending, stretching or other rolling of the optical fiber in the real field, we use this outer jacket so that it protects the optical fiber. So this is the typical construction of an optical fiber. So here we can see that the innermost layer, this is the innermost layer called the core. Core. And this core is surrounded by clad. This is the clad. So this is the cladding. Already we have mentioned here. So the second layer which is surrounded over the core is cladding. Again, between the buffer jacket and this cladding, there is a silicon coating. This is the silicon coating. Silicon coating. So this silicon coating is used to provide the improvement of quality in the transmission of light. And there is an layer buffer jacket which is used to protect optical fiber, which is used to protect the optical fiber from the abrasions. Here again one more layer is there, that is strength members. So these strength members are provides necessary toughness and tensile strength to the optical fiber. Next, the final layer is the black polyurethane outer jacket. So to protect from the hard pulling, rolling like that in the real field, real environmental things, it will protect the optical fiber. So this optical fiber will be protected by this outer jacket from the hard pullings or other which is in the real field. So here the total internal reflections happens between the core and clad. Between these two, the total internal reflection happens. So between core and cladding, the total internal reflections like this, the light is totally reflected back into the same area and will get the output. So as N1 is greater than N2. Okay, so the optical fiber works on the principle of total internal reflection. The total internal reflection is in between the happens in between the core and cladding. Between the core and cladding. Okay, this is the construction of an optical fiber. Firstly, there is a core surrounded by cladding, and then a silicon coating is there. Then a protective layer which is called buffer jacket. Use it to protect the core and cladding from the moisture or some abrasion. Then one more layer is there, that is strength membrane, strength members, and then the outer jacket. So this outer jacket is the final protective layer which is used to protect from the hardness, hard pulling or rolling something. So like this, optical fiber can be made. In the next session, we shall discuss about the acceptance angle and then form, and also we can see the numerical aperture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.